Hello, I'm Owen O'Malley, and I wanted to share this video about Hadoop and its ecosystem. I've been working pretty much exclusively on Hadoop for the last 6 years. My first patches went into the project before it was an independent project, and I have been a committer, a PMC member, and I was the first PMC chair for Hadoop. I was the architect for MapReduce and the architect for security, and I've touched all parts of the system. Hadoop is a project that lets you manage your big data, and what I mean by that is it lets you deal with high volumes of data, data that's changing rapidly, and a wide variety of data. It's not just a single open source project. Hadoop actually is a whole ecosystem of projects that work together to provide a common set of services. Hadoop transforms your commodity hardware, that's hardware that is standard enterprise-grade hardware, but without any of the extra reliability that you pay extra for, into a coherent service that lets you store petabytes of data reliably and also process that data very efficiently on lots of computers. The largest Hadoop clusters are up to 25 petabytes of data and 4,500 machines. That's a lot of processing power, and Hadoop lets you bring it all to bear on your application. The key attributes of Hadoop are that it's redundant and reliable. If you lose a machine, it automatically replicates your data without the operator having to do anything immediately. It's also extremely powerful. You can get the full access to your data. Your data isn't partitioned off somewhere where you can't access it. You have all the machines available to process your data and have very high bandwidth to it. It's mainly focused on batch processing. There are some pieces that are real-time, and we'll talk about those later, but primarily you're submitting an application to the cluster, it's running, and then you get the results back when it's done. It makes it very easy to write distributed applications. The distributed applications you can write and test on one machine and then automatically scale the same code out to run on 4,500 machines without changing it. That provides a lot of power and makes your developers much, much more efficient. Finally, it runs on commodity hardware. You don't need to buy special hardware. You don't need to buy expensive RAID systems or redundant reliability built into the hardware because we're doing all that reliability in software. Hadoop consists of two main pieces. The first is MapReduce. MapReduce is the processing part of Hadoop. It manages the jobs, and you submit your computations to MapReduce, and it will run it and give you your results. The second part of Hadoop is HDFS. HDFS is the Hadoop distributed file system, and it stores all the data for Hadoop. It has files and directories, just like you'd expect to see, but it scales out to many petabytes of storage. The MapReduce server on each machine is called the task tracker. The task tracker is responsible for launching your MapReduce tasks onto that machine. The HDFS server on the machine is called the data node. The data node stores the blocks of data that are stored in HDFS and keeps track of and provides high bandwidth access to the data. So that's what a single machine looks like. To make a cluster, you just replicate that pattern out. So you take a machine with a task tracker and a data node and make more and more and more copies of that. As you need more storage, you add another machine. As you need more compute power, you add another machine. Hadoop will scale out relatively linearly as you add more machines and gives you more and more bandwidth to your data, more and more storage, and more processing capabilities. MapReduce needs a coordinator. That coordinator is called the job tracker, and regardless of how large your cluster is, you have a single job tracker. The job tracker is responsible for accepting the user's jobs, dividing it into tasks, and assigning each task to an individual task tracker. The task tracker runs the task and reports the status as it runs and completes up to the job tracker. The job tracker is also responsible for noticing if a task tracker disappears, either because the software failed or the hardware failed. The job tracker notices that task tracker has gone away and isn't there anymore, and will automatically assign the things that were running on that task tracker to a another task tracker that's already in the cluster. The name node is the coordinator on the HDFS side. Just like the job tracker, there's a single name node in your cluster, and it provides the coordination for HDFS. When a client writes to HDFS, the client talks to the name node, gets told which data nodes to talk to, and then writes the data to those data nodes. When a client wants to read data out of HDFS, he talks to the name node, finds out where that file is, and then talks directly to those data nodes. It's important to notice that the data never flows through the name node. Only the information about where the data is located is on the name node. The name node, like the job tracker, is responsible for noticing when a data node has disappeared and automatically re-replicating the data. So you can see that for both storage and compute, we've got automatic failover. When a machine goes down, the computation and data automatically moved. That was managed by the job tracker on the name node. Now, to make a big cluster, you can scale this out to hundreds or thousands of machines. As I've said, the biggest clusters are 4,500 machines and store up to 23 or 25 petabytes of storage. What are the key characteristics of Hadoop? It's reliable. You don't need to worry about machine failures because your data is automatically held on multiple data nodes and will be automatically re-replicated if a machine fails. If a task fails or if the machine that a task is running on fails, that is automatically reassigned to a new machine. Hadoop is also very scalable. You can have one application that is running on one machine when you're testing and then automatically scale that same code to 100 machines, 1,000 machines, or even 4,000 machines. As you need more power, you can add more machines, and your same code will run at all of those scales. That adds a lot of power to your application. It provides very simple APIs for both compute and for data access, and it's very powerful. By dividing the problem up into small chunks, you can process huge amounts of data very efficiently, and you can recover from failures very quickly. Hadoop isn't just a single project, as we said previously. It includes a lot of other projects, and I want to cover some of those. The first one is Pig. Pig is a high-level language that translates down into MapReduce. You can think of this like a compiler. A compiler takes a high-level description of your program and converts it down into assembly language for you, so you don't need to worry about the details. Pig does the same thing for MapReduce jobs. Instead of having to write a whole chain of MapReduce jobs to get the processing done that you want, it allows you to write a high-level description of how the data is processed, hand that to Pig. Pig runs that and converts it into a MapReduce job and runs your application for you. As your developers get used to using Pig, you'll find that your productivity increases. At Yahoo, we've found that over half of the jobs are being run via Pig instead of being run directly into MapReduce using Java. People who aren't as comfortable with programming and want a more SQL-like interface, there's a top-level project named Hive. Hive takes a SQL-like language and does a similar transformation to Pig, where it converts it down into MapReduce and lets you define your computation in SQL and run it distributed across the cluster. At Facebook, they use it extensively, and it's used for 90% of their computations. Well, we've talked about Hadoop as being batch-oriented. That doesn't match all of the use cases that people need. People need to be able to read and write their data in real time. And HBase, which is a top-level Apache project, meets that need. It provides a simple interface to your distributed data that allows this kind of incremental processing. HBase can be accessed by Hive, by Pig, and by MapReduce, and stores its information in HDFS so that it's guaranteed to be reliable and durable. HBase is used for applications such as Facebook Messages. When you send a message to your friend in Facebook, that message is actually an object in an HBase table, and it scales out very, very well. HBase stores some of its metadata information in Zookeeper. Zookeeper is another Apache project that stores or provides coordination services for different servers. So if different servers need to work together, Zookeeper provides a very scalable solution that is highly available and lets them work together without worrying about all the details of whether they're cut off from the other masters or which master should be in charge. Zookeeper does all of that for you. Hive has always had a metadata store that stores the information about the tables in Hive that Hive can process. We wanted to make that same information available to Pig and MapReduce, and so we pulled the metadata server out of Hive and made a new project called hCatalog. hCatalog is just that metadata server with some improvements and enhancements that is now available so that all applications can access it. hCatalog can reference data in either HDFS, which is the standard case, or in HBase. All right, so now you can see all the pieces together. These form the core of what people refer to as Hadoop. You can see Pig, Hive, HBase, Zookeeper, hCatalog, MapReduce, and HDFS. There are also a lot of other projects that people use with Hadoop. The first one is Mahout. Mahout is a machine learning library that lets you write MapReduce applications focused on machine learning. There are also ones that help you understand what's going on in your cluster. Ambari, Ganglia, and Nagios provide that kind of access. Scoop is a tool that lets you run MapReduce applications that pull information or push information to or from SQL databases. So if you need to get your information into or out of MySQL or Oracle, Scoop is the tool to look at. Cascading is a high-level tool that provides, translates down into MapReduce. So you could think of it as equivalent to Pig or Hive. Oozie is a workflow coordination management. So you define when you want your MapReduce jobs to run, and Oozie will fire them off automatically. It can also trigger when data becomes available and, again, launch your MapReduce jobs on that new data. Flume is for streaming inputs into Hadoop. So if you have servers that are generating data continually, you can use Flume to get that data loaded into HDFS, where then it can be processed using MapReduce, Pig, or Hive. As Hadoop is obviously distributed, and so we need to have the different pieces talking to each other. And so we support the three most common serialization libraries. There's support for Protobuf, which came from Google, and Avro and Thrift, which are Apache projects. Most of the access to HDFS is through the Java library, or there's an equivalent C library. However, some people need to access it through their native operating system, and so FuseDFS provides Linux access so that you can use your standard Linux tools to access your HDFS files. Thank you very much. I hope you have enjoyed watching this training video, and please check out our other Hortonworks training videos on our website. Thank you.